And to kick us off, David Rapetti will be telling us about the galactic foreground. I should say, I forgot to say, all of these are, of course, expanding upon Jack gave an invigorating talk this morning about radio astronomy from the moon. So this is a session that goes more in depth about possibilities for radio astronomy from the moon and the lunar environment. And the first one, we'll be talking about one of the aspects of extracting the science. David Rapetti will be telling us about the data analysis pipeline. So David, over to you.
All right, thank you, Joe. So yeah, as you mentioned, I'm going to be talking about our data analysis pipeline for a lunar-based satellite to study the early universe, as Jack discussed this morning and the administrator referred to yesterday as well. And to do that, we're going to be using the hyperfine line of neutral hydrogen, and in particular the sky average observations of this line, what we call the global 21 centimeter signal. And these are the two main challenges that this observation face. So first of all, this signal is very small compared with the foreground. This is 4 to 6 orders of magnitude larger, the foreground. And the second challenge that we have is that we have limited information on both the signal and the systematics. Being the systematics, for example, when I'm going to be focusing on this talk, would be the beam-weighted foreground. And this also includes the overlap between the signal and the systematics. And for example, for the signal, we have codes to describe the cosmological and astrophysical origins of this signal, but there's a variety of them. And recently these have been expanded due to a claim trough at 78 megahertz by the HS team that could be the cosmic dawn measurement that we're going after for that period that we see here in gray. This is when the first galaxies and first stars, galaxies, and black holes turn on to the universe. But in conjunction with that, and I must say as well that this measurement is 2 to 3 times deeper than expected by the standard model that we can see here in the dashed line, which means that this could point to exotic physics, as Jack also referred to, but also this could be due to the systematic, so we don't know that. So one of the points of the dark ages polarimeter pathfinder, which is a small submission concept that Jack discussed as well, is to verify this measurement and improve the precision and accuracy of this measurement. And to do that in conjunction with the measurement of the dark ages trough that we can see here in this plot at higher redshifts, which can offer us the possibility, as this plot shows, to break the degeneracy to investigate these astrophysical and cosmological origins for the dark ages, since there's no astrophysics yet, and then in combination with astrophysics in the cosmic dawn. So in order to do that, we designed a new pipeline in order to face these challenges that consist on developing training sets and use pattern recognition tools on these training sets. So we developed training sets for each of the components, for the signal and for the systematics. And we can see here the two types of training sets I'm going to be focusing for this talk, which is for the signal and for the beam-weighted foreground. On the left, we have the signal that we have, for example, a bunch of lines here generated by the ARIS code, the physical code to generate these kind of signals. We have also a phenomenological model, which is the Tench model. And from that, we can actually extract eigenmodes using the singular value decomposition technique. We can do the same thing for the foreground, for the beam-weighted foreground on the right. And we can see here the different Stokes parameters, since being the foreground anisotropic, we can measure actually induced polarization and use this induced polarization to distinguish from the signal, which is isotropic and unpolarized. So this is one of the key features of our pipeline compared with the traditional methods, which allows us to do these separations and to use the benefit of these different experimental designs straightforwardly and rigorously. And not only that, not only polarization, but also the foreground changes in time, which the signal does not. So this time dependence also can be captured by our pipeline. And you can see more on that as well on the Keith Tosher poster in the tomorrow session. So we can use this pipeline to separate these two components very powerfully. So in order to do that, we need a training set, which Joshua Heber will discuss, in particular training set for foreground after me. And of course, these training sets need to be accurate. This is something that Neil Bassett has a poster on as well. So once we have these modes, this is the first part of the pipeline. We need to select the number of modes. We do that with the information criteria. And once we have that, we have our initial constraints to get into MCMC fit. This is a nonlinear fit. We can choose a single model, which is normally going to be nonlinear, and we are going to constrain the parameters, the physical parameters that we're interested on, while we're keeping the linear modes from the foreground, which normally are very large. And we can do that analytically. We can marginalize these modes analytically. So these give us a large advantage in efficiency, and I'll show you in a moment how many modes I'm talking about. And this is an exact calculation. This is an exact calculation that allow us only to MCMC the signal parameters and to marginalize analytically over the foreground modes. And I'm showing here some results based on a model inspired by the edges measurement. This is a flattened Gaussian model. And we can see on the right constraints in blue from the linear part of the pipeline, which we use as an input for the MCMC, and then in red are the nonlinear constraints from the MCMC, which are tighter due to the fact that now the overlap between the signal, which is nonlinear, and the model is less. So these are the kind of constraints that we can get for the signal parameters in this particular model. For example, we can see here two different cases since we don't know how the signal looks like. We can see that depends on how the signal looks like and how it overlaps with the foreground, which is in this case our systematics here, the weighted foreground. We can see on the left that when the signal does not overlap that much with the foreground, the green and the blue constraints, which are the full parameter uncertainties, are relatively close to what we would obtain if we would have only a statistical noise for this calculation.
David, 2-minute warning.
All right, but if we have a case where the overlap is larger, like as we see on the right, then these uncertainties, which probably include this overlap, are larger than what would be for the noise level. We can see the same effect here. So this is the reason why we are seeing larger uncertainties. The correlations on the left are larger than the correlations on the right. This corresponds to the same MCMC fits that we are seeing before. Okay, so you can see here the correlations of the foreground and the signal. You can see that the signal is only 4 parameters, while the foreground is 160 parameters. So these 160 parameters do not need to be MCMC'd, which is more expensive. So we go from 164 to 4 parameters. And we can see here the correlations, and we can see that not all the modes correlate. The gray areas are the ones that basically don't correlate as much. So don't need to worry about those ones. So we can see which modes matter. And this is when we actually use foreground priors. You can see more details on that on the paper. We use this technique instead of using an information criteria in this case. And the last thing I want to mention is what happens if we go to a little bit more sophisticated model than the flattened Gaussian, which allows us to, this is a phenomenological model as well, but allows us to describe both the cosmic dawn and the dark ages. as we are interested for Dapper. And here we can see also what happens when we increase the integration time, when we're going from something typical from the current experiments in the ground, 800 hours, to something like more like Dapper, 4,000 hours, to something like more like maybe we could get with 100,000 hours for Farsight. We can see here the reference to the code. And let me say as well that we don't see here with this current setup any systematic flaw going to this amount of integration time. And just to summarize that, you can see here the benefits of our pipeline as I've been describing during the talk, and I'm going to leave that here, and then you can also check it out later in detail as I've been describing its talk, what our new pipeline compared to the traditional pipeline can get us. Thank you.
Thank you. Neil?
Great, yeah, thanks, David, for that talk. So I think we do have a little bit of time for questions. So just as a reminder, there's kind of two methods to ask questions. The first is that you could raise your hand, which you can do by going down to the participants tab at the bottom, and then I can call on you, in which case you can unmute yourself and ask your question. You can also put questions in the chat. It seems like we have one, which may have been answered, but I'll read it aloud for David just so you can respond to it anyway. So Mark Kleinvold says, "Dear David, very interesting technique, and I hope that in the not too far future, we can provide you with the data from our instrument behind the moon. But have you also considered using data from EDGES and related projects?"
Yep, this is an excellent question because we're doing exactly that. So we are applying this technique to the EDGES data currently. So we've been already doing some of that with the release data, as was shown in a paper led by Rich Bradley, with an idea about the effects of round plane on the as a systematic on the results of the from EDGES. But we also doing that currently with the release data in collaboration with the EDGES team that we've been actually looking into for a while. And we actually in the process of data selection and applying these kind of techniques, and in particular as well, the minimum assumption analysis that you can see also a paper by Keith Tosher recently, where we actually don't need to even use a signal training set in order to not bias our results.
Great. I think it's time to move on to the next speaker, but thanks again, David.